Hello and welcome to Control F, the NSI Cyber and Tech Center's new podcast that features season-long groupings of issues at the intersection of technology and national security. Our first season of Control F is focused on game-changing technologies through a set of 8 episodes released every other week over the course of 4 months. Each of these episodes takes a deep dive into the key emerging technologies that are reshaping our world and the ever-evolving tech policy landscape alongside them. During each episode this season, we're featuring one or more leading technical experts in a given field, as well as one or more key investors funding the development of these critical technologies. So today, we're talking about quantum computing, the technological capability that combines computer science, mathematics, physics, and specifically the principles of quantum mechanics to solve some of the world's toughest problems that traditional computers, even supercomputers, can't solve. I'm joined by two fantastic experts in the field today to unpack how quantum computing works and is changing the way that we address some of these problems, including the national security domain. So first, I have Dr. Stephen Flammia. He's the director of the Center for Quantum Architecture and Software Development, and is a quantum computing lead at Virginia Tech's Innovation Campus, as well as a professor of computer science in the College of Engineering at Virginia Tech. In his role at the new center that's based here in Northern Virginia, he drives strategy and is responsible for building the new center's team, including hiring additional faculty scientists and growing connections to industry. Prior to joining Virginia Tech, Dr. Flammia spent 3 years serving as a principal research scientist at Amazon Web Services, Center for Quantum Computing in Pasadena, California, my old hometown, although I grew up in Santa Monica. Prior to that, Dr. Flammia served as a professor at the University of Sydney in Australia and completed postdoc research at Caltech in Pasadena and at the Perimeter Institute for Theoretical Physics in Waterloo, Canada. Over the course of his career, he's published more than 80 articles in peer-reviewed journals and garnered over 10,000 citations. He's a winner of the Pawsey Medal and is a fellow of the American Physical Society. Several of Dr. Flammia's theoretical results have led to experimental breakthroughs in the characterization, verification, and validation of quantum devices. Dr. Fiona Murray is the Associate Dean of Innovation at the Sloan School of Management at MIT, where she holds the William Porter Professorship of Entrepreneurship. Dame Fiona advises the British Prime Minister's Council on Science and Technology and has been honored as a member of the Order of the British Empire for her UK contributions. Dame Fiona is also a member of the Ministry of Defence Innovation Advisory Panel in the UK, as well as a member of the European Innovation Council's Joint Experts Group, and sits on the boards of Spark Cognition, Mass Challenge, and the NATO Innovation Fund, a venture capital initiative that is deploying over 1 billion euros across critical deep tech sectors for the NATO alliance. Among other things, Dame Fiona's work focuses on transforming science and technology investments into startups that can address global challenges. So we've got an amazing group of experts here to talk to us today about quantum computing. So let's just jump right in. So I'll start with you, Dr. Flammia. Help us set the stage in terms of the technology, right? And let us level set here on sort of this game-changing technology, right? Describe for us what quantum computing is in terms, like a layperson can understand. And in particular, what are the core principles that differentiate quantum computing from classical computing?
Right. So you already used a jargon word, which is classical computing. Classical computing just means computers that are derived from technology of the present day computers that you and I use, our laptops, our iPhones.
Yeah.
So quantum computing is technology which is based on computations that fundamentally use quantum physics to do those computations. And so quantum physics is the physics of very small things. And of course, our computers that we use have transistors, which are very small. But fundamentally, the way that they store and process information treats it as if it doesn't matter so much that it's very small things that are being processed. You could, in principle, do those same computations using macroscopic objects like coins or something like this to store that information. So quantum mechanics, let me give an analogy. Quantum mechanics, being the science of atoms and molecules and single photons of light and things like this, if you think about water has emergent properties at large scales. It has waves and things that we're all familiar with.
Right.
But individual molecules do not behave the way that we expect. So quantum mechanics is very counterintuitive. Quantum computing uses the physics at that atomic scale in a fundamental way to process information. That's at its heart is what it is.
Okay, and so when we talk about sort of quantum mechanics and how it enables quantum computing to solve problems that are too hard for traditional computers, my laptop, right? Even a supercomputer, Cray supercomputer, whether that's at NSA or at IBM. What's different about quantum mechanics? I know that, sort of normal computers or whatever computers that we use zeros and ones, right? And I've heard there's this idea behind quantum mechanics of quantum states, superposition. What is all that about, and how does that enable quantum computing?
So yeah, that's exactly right. Quantum computing is using superposition. That's one buzzword you used. And another one is entanglement in order to do things that are fundamentally not possible classically. So in a classical device, you can only have two states in which to store information. Let's say 0 and 1. You could have more, but you can always mock that up by just having a few more zeros and ones. So all of our classical information processing tools just use 0 and 1 to store the information. Quantum mechanically, you can have these things called superpositions. Now, superposition by itself is not completely unintuitive. If you play music or go to the beach, you can see superpositions of waves. So this just means that there's more than one structure sort of sitting on top of itself. Waves can be in superposition in exactly this way. However, there's this other phenomenon that I mentioned called entanglement. And when you combine entanglement and superposition, you get really strange things that don't have classical analogs. So entanglement is rather hard to explain. Inevitably, any analogy that one gives that avoids mathematics is going to be a little bit lossy. So with that caveat, entanglement is a way in which things can be correlated, but in a stronger sense than we've ever really experienced in our everyday lives. So what is correlation? Just to remind you, if I take two coins and I place them on a table, both heads up, let's maybe say I put some clear packing tape around them or something, I can flip them as a pair, right? They're taped together.
Right.
They're always going to be either heads or tails when they land, and that's it. So they're perfectly correlated. With entangled states, that correlation persists even if you split them apart, you cut the tape in half and move them very far away from each other. So this is a sort of correlation that persists across space and time in interesting ways. It also persists in other ways when you can observe these two coins. You can sort of probe them in different ways and you still see the correlation in ways you wouldn't expect. And so this is like a more powerful, because this is something that we don't observe, you can think of it now as a resource that we can exploit to try to do computation in new ways. And that's what quantum computers take advantage of. That's one of the ways that they take advantage of quantum physics.
Interesting. I do want to come back to this question of how these sort of two states interact with each other and how that enables this quantum computing. But before I do that, I want to go to Dame Fiona and ask her, Dame Fiona, you have this unique position because you're both at one of the most innovative universities in the world, MIT, but you're also an investor in this, or you're on the board of an investment fund that's focused on spending, over €1 billion on allied technologies. Talk to us about the promising investment opportunities that you see, both coming out of research at MIT, but also as the NATO Innovation Fund thinks about where it's going to invest in this quantum domain. Are there particular applications that you think might be most interesting or exciting in the quantum domain?
Mm-hmm. So certainly, I mean, quantum, I think, is something that has animated everybody from the sort of those who understand this from the deepest sort of realms of physics all the way through to those of us who understand the buzzwords and everything in between. We know that a lot of the work that's happening around quantum computing is happening in some very special places in the world, in these innovation ecosystems, places that bring together universities, startups, risk capital providers, but also the government and very large corporations. And I think the question is really, what are the opportunities that we're seeing? What's going to be at the forefront? Where can we see immediate or at least medium-term impact? That's something that's going to propel investment dollars into these areas, really focus the attention of startup entrepreneurs. And where is it that we're going to need to continue to build those intellectual foundations? And that's the role of the university, of national labs, of the governments, and so on. I think as Steve has already described, quantum computing helps us deal with some really difficult problems, but also problems with some distinctive characteristics and characteristics that are about their probabilistic nature and what have you. And so I think when we start to look at where they're likely to be applications, we're certainly thinking about things like the pharmaceutical industry, where we continue to try to solve really hard problems about understanding how cells work, how proteins fold, and so on. I think if we take that a step further, we're thinking about material science. We know that there's some really critical minerals and very, very important materials that propel our economies, whether that be in batteries, whether it's the sorts of magnets that we need in fusion reactors and so on. Those are hard materials to generate and to develop. If we can optimize those using quantum computing, that will be extraordinary. And of course, in finance, lots of very, very interesting finance problems. And so those are some of the more immediate term areas. And so it's not surprising that we're beginning to see large corporations as well as startups focused on that application space. We've
Interesting.
also got to make sure we invest in the domains and the foundational hardware as well, because none of the software is going to work unless we actually have hardware that can put all that quantum physics into useful action.
Right. No, that makes a lot of sense. And one of the things you've hit on is that some of these key areas that have been very much part of the national security debate just in the last few months and years: critical minerals, right, applied science research, and the like, finance. These are all issues at the core, I think, of the sort of ongoing challenges we face in the world. Some of our biggest peer competitors or near peer competitors, whether that's China or Russia, right, and whether we're talking about the NATO alliance or the United States-UK alliance. So as we're thinking about these spaces, do we worry that that the ongoing research that we're seeing in quantum is taking place only in these particular bubbles, right? So you describe them as innovation ecosystems, a set of universities, a set of special places. Should we be thinking about this from an alliance perspective, or should we think about this on the global perspective, or is it a little bit of both? How do we sort of think through that, Dame Fiona?
Yeah, so I think what we know is that innovation is actually extremely concentrated in some very special places around the world.
Yeah.
But the expression around the world is really what matters. These are places in the United States, across Europe, across our AUKUS relationships, but also obviously in adversarial countries. And there's no reason for us to believe that in China there aren't equally vibrant innovation ecosystems, albeit ones with a very different sort of intent focused on this kind of activity. And so we need to both understand what's going on in our own ecosystems, but keep a very, very close eye on those of our adversaries and make sure that we don't sort of fall asleep and not significantly invest in what's happening. I think the other tension that we see is every single country is thinking about what it should be doing with respect to quantum computing, both in terms of funding the basic research foundations at national labs and universities, but also building entrepreneurial startup ventures focused on crowding in risk capital into these spaces and so on. And yet, I think if we really focus too narrowly on that sort of small yard, high fence kind of view of the world, we're going to miss something, I think, because we're going to have duplicative activity across a set of allied nations. And so I think instead what we're going to have to start to talk about is really building what I would think of as shared gardens. So instead of a sort of a small yard, can we have some shared gardens, still with fences, but where we're really working across allies? Because there's enough work to be done. There's enough talent that we need to generate. There's enough different types of companies and different focus areas that I think having that plethora of opportunities and plethora of activities, a portfolio, if you will, across these innovation ecosystems is going to allow us to be more effective against our adversaries.
You know, it's interesting, Dave, you raise that point. And I do want to come back to Dr. Flammia and talk about some more of the technology here. But just on the point that you raised, you know, we learned this lesson back in the post-World War II era as we developed the sort of the Five Eyes Alliance. We can now talk about that. It used to be back in the day you couldn't even talk about the Five Eyes Alliance. But we did have this idea of shared gardens. And when it came to signals intelligence, we shared openly with our Five Eyes partners and worked collaboratively. It sounds like what you're describing is in this domain, quantum computing, and maybe some other areas of leading edge technology, we need to be thinking about it more as an allied effort than just a US or a UK or individualized country effort. Am I hearing you right?
Absolutely. So I think what we need, if we take the shared gardens analogy, we're going to really have to think carefully about what the right sets of alliances are. We don't necessarily, we may decide as individual countries that there are certain things that we wish to have as sovereign capabilities, and those may be fundamental to each of our nations. But frankly, we're going to have to do this across relationships, across allies. We're going to have to work in these new collaborative ways because there's so much to be done that I don't think any one country, even the United States, can do this alone.
So, Dr. Flammia, one of the things that Dame Fiona put on the table was this idea that there are multiple technologies, and we're not sure which one of them might succeed or be the most capable, most efficient in this domain. Talk to us about the range of technologies that are in play here, and whether we ought to focus on one particular capability in one area, or whether it makes sense to actually have a portfolio of investments the way Dame Fiona described in order to ensure that we're able to pursue whichever or multiple technologies that might ultimately get us to the goal of sustainable, efficient quantum computing.
So I think absolutely the right approach is to fund several different technologies right now. There are lots of different promising technologies. And importantly, if you just look at the track record of quantum computing over the last few decades, there has not been a clear winner that has sustained their lead for any given amount of time. Some of the important technologies include trapped ions, superconducting qubits, and in recent years, neutral atoms has really has had some very impressive results. And I think 10 years ago, that was really not the case. The research in neutral atoms did not look like it was going to be as promising to catch up to what was happening with superconducting qubits. So unlike with classical computing technology, where about shortly after we had developed the transistor and integrated circuits, it became clear that there was a technology that we could rally around that would sustain long-term innovation for multiple rounds of innovation, repeated rounds of innovation and improvement. It's not really clear that that's the case yet with quantum computing. To just pick on one specific example with superconducting qubits, there are pretty difficult limitations in the fabrication process of these devices that we're slowing down in terms of how much we can improve these devices at the moment because of limitations in how well we understand the material science of fabricating these devices. So that doesn't mean it's going to stop. I hope that superconducting qubits will eventually be used to make quantum computers, and maybe they will. I'm just saying that I think it's a challenging problem, one where you can't simply, it's not a straightforward problem where we're going to build this device and then we're going to tune these things, build a better device and a better one. It's not obvious that there's going to be Moore's law style improvement in these devices. So I don't think that's true for any of the technologies that I mentioned, nor a few others that I didn't mention, like photonic quantum computers, for example. So we're kind of forced to be in a position where we have to hedge. But I think this is actually a good thing for a number of reasons. These different platforms, even if one does eventually come to dominate, this isn't necessarily wasted effort because some of these platforms might be better at certain niche applications. So for example, trapped ions tend to have very good connectivity compared to superconducting qubits. So the connectivity just means that if I want to do a special quantum operation between two constituent quantum bits inside my device, I have rather immediate access to that. Whereas with superconducting qubits, it might be a lot harder to get to distant things across two different parts of the device to interact in the way that you're trying to engineer. There's also other technologies. It's not just about computers. There's also a quantum internet that will need to be built to transmit quantum information from node to node. And it might be that some technologies are better at transducing information from one form so that it transmits. I mean, photons are the preferred mode of transmission of information. So we're going to need to develop all of these other quantum technologies. We would be shooting ourselves in the foot if we were to try to prematurely commit to something now. So we should absolutely fund multiple technologies for the foreseeable future, for as far as I can foresee, which is at least 5 years.
So Dame Fiona, if you and Dr. Flammia are right that we need to have a portfolio of techniques that we invest in, right, this could get very expensive very fast. And as powerful as €1 billion are for the NATO Innovation Fund, this is going to require a lot more capital, not just NATO money, not just U.S. government money or other national government money, but to your point, it's going to require a lot of private capital to come in as well. Yeah. How do we think about incentivizing that private capital investment and making sure it's directed in the right direction and doesn't benefit ultimately adversary capabilities as well?
Yeah. again, I think you're exactly right. If we're going to invest in these different flavors of quantum computing, and there are multiple of them, as we just heard, each one of these companies is going to require, billions of dollars. And so that does get quite expensive quite quickly. It means that I think we've got to invest across the piece, across a variety of types of alliances. We absolutely need to crowd in private sector capital. I think the private sector is beginning to move into this space because they do see that these markets are going to emerge. I think if we can start to create those markets through government contracts, government procurement, dare I say it, as well as some of the leading large corporations who can really see benefits, whether that's in pharmaceuticals, material science, finance, etc., that's going to help us move these markets. I agree with Steve. We absolutely don't know what the winner is going to be. And I'm not sure that we think that this is going to be a winner-take-all market. If you think back to the 1920s in the auto industry, you actually had gasoline and electric vehicles. Gasoline vehicles won in that era. Right. I think in quantum computing, we're going to see different kinds of approaches for different sorts of problems. And frankly, we'll see different kinds of approaches yielding to the engineering issues probably more easily from one to another. That does mean quite a lot of capital. It'll also mean various moments when there will be winners as well as losers. We will, I think, see quite a lot of mergers and acquisition activity. We haven't really got to that point yet. And we'll need to be quite creative about making sure that the intellectual property and the talent, frankly, doesn't get into the hands of our adversaries when those moments happen. So we'll need to really make sure that those fences that we need to build around our shared gardens are actually configured so that we keep the talent, the capital, and especially the intellectual property kind of amongst allies.
Yeah. Dr. Flammia, one of the things that that Dame Fiona just talked about was this idea of specific areas where quantum computing can contribute to innovation. And one of the areas that we always hear a lot of talk about is encryption, and the fact that quantum computing is going to give us the ability to break classical encryption. I know you use the word classical again, but talk to us about how quantum computing works, how these qubits work, and how they enable the kind of computations that will allow us to, quote unquote, break classical encryption.
Right, so maybe it's best to just explain a little bit how one of the most popular classical crypto systems works, which is RSA.
Great.
So the RSA crypto system works based on the presumed hardness of factoring very large integers. So you'll recall how integer factoring works. If I give you two numbers, first of all, how does multiplication work? I give you two numbers, 3 and 5, you can just multiply them to get 15. It's a little bit harder if I give you the number 15 and I ask you to break it into whole number factors, specifically prime factors, that is, those numbers that are divisible only by themselves in 1. So when you try to do this with very large numbers that if you were to write them out in digits might be 1,000 digits long, these numbers are thousands of digits long, like 2,000-bit RSA. So, these types of numbers are very hard to factor on a classical computer. It turns out that there's an algorithm known as Shor's algorithm due to Peter Shor, about 30 years old now, this algorithm, a little more than that, which on a quantum computer, on quantum hardware, you can factor integers efficiently. So much faster than what the best classical algorithms can do running on the best classical hardware. Now, we don't have hardware, unless it's in some classified place that I don't know about. We don't have hardware that can run Shor's algorithm yet. But the theoretical existence of this algorithm has upended a lot of thinking, right? When things are encrypted or when things are labeled secret or top secret or whatever, there's an expected lifetime before an adversary might be able to crack that secret and read those messages. And if I were to develop a quantum computer tomorrow, then I could break things that had been encrypted but intercepted as encrypted text, as ciphertext. I can now read them before their shelf life has expired, before the value of those secrets is deemed no longer valuable. So they do it. I mean, I don't know that it's valuable to go into how Shor's algorithm works. The fact that it exists is, the fact it exists and it fundamentally exploits properties of quantum computers. There's no way to make it sort of fully classical as far as we know. And so, go ahead.
Well, no, the question I was going to ask, and maybe you were going to get to it right now, was so I understand that it can sort of break classical encryption, but what is it about quantum computing? What is it about sort of the qubits or the superposition or whatever?
Hmm.
I know it has something to Schrodinger's cat, the cat in the box that's not alive or dead, right? Maybe I'm wrong
Yeah.
about that, but I know there's this right. There's this thought experiment.
Okay.
Is there a particular aspect of quantum mechanics or quantum computing that allows you to do the kind of
Yes.
computations that result in this ability to break
Yes.
classical encryption?
So specifically, I would say one of the things that quantum computers are really good at is finding certain periodic patterns.
Hmm.
So one of the core subroutines in Shor's algorithm is called period finding. So what this is I give you, let's say I give you a signal of some kind, so you're intercepting some signal and you can see a waveform on your radar or whatever, and it has some period. It repeats itself every so often, and you want to know what is that period. It sounds like a very easy thing to do, actually, because you think, well, I just look at it and I can just see. But it's really, if you imagine something quite wiggly, it's really not so obvious how you would do this, and it's especially not obvious in other contexts. Specifically, if you place this problem into the context of um, numbers, which are if you place this
Very
into the
large.
context of
Yeah.
very large numbers, which have a period when you do what's called modular arithmetic. Um, so what they're really able to do is harness wave-like properties in some essential way that quantum materials have
Hmm.
to find periods much faster than what we know how to do on conventional or classical computers. So this is like at the heart that drives Shor's algorithm and several other related algorithms as well that also give what are known as exponential speedups. They go exponentially faster than the best known classical algorithms that we have for these problems.
So, Dave, Dr. Flammia has talked about these sort of theoretical innovations like Shor's algorithm, which today, as he describes, unless there's something in a classified room we don't know about, we're not able to implement today. And we're always talking about, quantum, I've heard about quantum computing now for the better part of a decade and a half. It always seems like it's, 5, 8, 10 years away. But it does seem like we're hearing more about it. It does seem like people are more concerned. You've got the U.S. putting out and NSA putting out quantum proof encryption or quantum resistant encryption capabilities. What is making quantum more investable today? Is it really nearer in time than we've had in the past, or is it just feel like it is? I mean, do you think it's more investable today than it's been in the past?
I think it's more investable today for two reasons. The first reason is I do believe that it is nearer today than it was in the past. I believe that we are making actually very significant progress, and I think we're making enough progress that if I am sitting in a government department, I need to be able to have a series of different quantum computers. I need to be able to try out the emerging quantum computers that are being built to see how
Right.
they work, to see whether they are actually capable of doing the things that we can theorize about. I think that's one of the reasons there really is meaningful progress. I think we're actually moving quite significantly from an era of quantum physics to an era of quantum engineering, where we've worked out quite a lot of the physics, and we're now trying to work out whether we can engineer a system at scale to do this. And we're seeing that in the way we're starting to train individuals. I think the second reason why we're hearing more about this and we care more is that we are in a state of heightened geopolitical competition and geopolitical tension. We know very well that our adversaries are quite technically sophisticated, although perhaps we don't always know quite how sophisticated they are. And so if that's true, then we absolutely need to be on the front foot. And so we can't wait and see what emerges in, a calm and peaceful world. Actually, we have to get as far out as we possibly can to make sure that we are in a position to decrypt the things that matter to us, but we're also in a position to do post-quantum encryption to make sure that the things that we're generating are also safe. So those two forces, the fact that things are moving from sort of physics to engineering, and that the world has moved from being somewhat peaceful to being it's a raised state of geopolitical tension, I think means that we have to take this extremely seriously. And all those 5 players in the ecosystem need to do their part in a fairly, in a collaborative fashion.
Yeah. Dr.
If I could
Flammia, I
just
mean,
add, can
yeah,
I add to that?
please.
I think one other reason, I mean, I agree with the comment that it suffers from this quantum computing is 5 years away and always will be, or some such criticism that's been leveled at other technologies like fusion, which I hope will have a moment soon. It's looking more promising lately. It's a side point. Quantum computing, very similar actually to fusion, has a tipping point, which you can quantify your approach to it. And this is what's called quantum error correction, which is the point at which all the errors and failures that happen in prototype devices that make them not sound as computers, they eventually fail. There's a tipping point where you can correct those errors faster than they accumulate. And when that happens, it's basically, it's another one of these exponential levers. The history of humanity is littered with the bones of people who misunderstood exponentials and their growth. I'm saying this to you who has some training as an economist. I don't think I have to emphasize this. Once you can correct the errors faster than they accumulate, it's off to the races. It really is. And so there are encouraging signs. It's not just one number that has to meet this tipping point. It's several different things. Dame Fiona mentioned that it's an engineering problem increasingly. And it's true that with engineering, you need to achieve this, 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 and this. And so there have been a lot of demonstrations that have achieved subsets of these goals, but not all of them simultaneously. But it's feeling increasingly inevitable that we will reach this tipping point, and it's just going over the falls. You can't stop it after that. So I think it is important that we think about these things for that reason.
Yeah. So given that, and given it, so it sounds like you agree with Dame Fiona that we're moving from this idea of quantum physics into quantum engineering, and that we're it sounds like you're describing it that we're nearing that tipping point, just like with fusion, where the amount of energy you extract is greater than the amount of energy you're putting in. If you can correct quantum error at the right level, you can finally get to the point where now your capability explodes. As we're thinking about that, are there particular areas of research, whether basic or applied? And I'm going to come to you, Dame Fiona, to ask about it on the investment side and the capabilities side. But are there particular areas where you see a need for a particular innovation or capability development now, or areas that are on that tipping point and are about to tip over that we should all be watching for as a sign that we're nearing that point, Dr. Flammia?
Yeah, that's a great question. And I would say too that the analogy with fusion is actually quite good. Even if we reach the tipping point with fusion today or tomorrow, there's still the issue of whether or not it's cost effective to get your power from a fusion reactor. So it's not obvious that even achieving that amazing milestone, it will be one of the most amazing achievements of humanity if we can achieve fusion, controlled fusion reactions. Ditto for quantum computing. It will not be immediately economical to solve your problems on quantum devices. They will still need to scale up. You're running against a competition who's had a huge head start, decades of head start, trillions of dollars of investment. So, but you have this exponential wind in your sails.
You mean classical computing?
I'm talking about classical computing. Yeah. Moore's law, doubling the transistor density on chips every 18 months for decades. So you can catch up with that if you have exponential wind in your sails, which you get from quantum computers. But it's not, even if tomorrow the cover of some magazine or New York Times or whatever says we did it, we're correcting the errors faster, it's not, there's still going to be some headway. So back to your question, what are the most promising applications, I believe was your question. Is that right?
Yep.
So in my opinion, there are several. One of them is going to be actually simulating other quantum systems. It sounds kind of silly to go and build a quantum system just to simulate other quantum systems, but honestly, a huge amount of our technology base is contingent on our understanding of things like material science and chemistry, pharmaceuticals, things like this. So I think one of the major application areas is going to be to understand quantum materials better. We have, again, decades of experience from classical computing, from countless brilliant researchers studying these problems that allow us to continue to make progress in chemistry and in material science. But a quantum computer, if it were economical to use one, would rapidly speed up that feedback loop. currently, if you're studying materials, there is a simulation that you can do to try to study materials. It does not always get the correct answer. You have to make certain uncontrolled approximations to try to model the material in a way that will fit your simulation onto a computer, even a supercomputer, to fit it within the time and space constraints that you have to model that material. Quantum computers are just much better suited to simulating material properties and things like this. It's native to, you're doing it on its own firmware, so to speak.
Yeah.
So you can really accelerate computations in this space. Another space which I think is more skeptical, but I'm cautiously optimistic for, is optimization type problems. So Dame Fiona mentioned things like applications in finance. I would also say industrial type applications. It's very common to see in industrial applications things like a scheduling problem, right? So like, how do I schedule these various resources in an optimal way so that these machines aren't idle, or I minimize the amount of time that they're idle, or things like this. So that's a very common problem that you see among large scale industries, automakers, people like this. It's known that there are theoretical speedups that quantum computers can offer for these problems, but I would say it's largely not clear still. We need more research into the question of whether or not we can genuinely speed these things up in a relevant timescale, or whether we could simply, it maybe takes the same amount of time, but the quality of the solution is better. So the amount of schedule reduces a little bit. Yeah. So it still takes you however long as it took on your classical device, but the quality of the solution is better. Even a 1% improvement could have a dramatic impact on the profit margins of a large scale company if you could do it on a quantum computer. That I'm optimistic about, but it's really unclear what the timeline is for that. I'd say for near-term applications, it's going to be things where we're genuinely simulating quantum materials is the most likely application, in my opinion.
So Dame Fiona, both you and Professor Flammia have laid out this idea of material science. He's laid out particularly in the quantum sort of quantum arena. You've also both talked about this potential for industrial efficiency gains or financial gains in the finance sector as well. And so it brings me back to this question we talked a little bit about earlier, right? This idea of this capability being core to both economic and national security for individual nations, and in particular, groupings of alliance nations. In this case, in the case of NATO, the U.S. Atlantic, U.S. European alliance, and maybe a broader alliance around the globe. So, coming back to your role at the NATO Innovation Fund, this $1 billion deep tech fund that's going to be investing in alliance technologies, talk to us about how you all see the investments in quantum, given that there are these broad scale, potentially, game-changing innovations when it comes to economics and our national security. Is that the right way to think about this? And if so, how is NIF, the NATO Innovation Fund, thinking about these problems?
Mm-hmm. So, of course, the NATO Innovation Fund, we have an amazing team of investors, and the board leaves the individual investment decision making to them. But as a team, and as a broader team working with the various NATO members who are participants in the fund, we're thinking very, very hard about the strategic technologies that are going to be profoundly important to the future of the alliance. And we talk about investing in defense, security, and resilience. And I think that's actually quite a useful framework in general. It's also quite helpful when we think about it in the realm of quantum computing. So if you think about it as resilient, we will create more resilient economies if we are investing in some fundamental strategic technologies. And so that does mean investing in quantum computing. We have to recognize that there are multiple flavors at the moment of quantum computing, whether we're talking about superconductivity or trapped ion and so on. And it's too soon to say which of those is likely to be successful. And so across the piece, we're going to have to make sure that there is investment coming from a variety of different capital providers into those strategic foundations. If we go one click out from there, we think a lot about the strategic supply chains. Sometimes people talk about these as some of the choke point technologies. So what are the technologies that we need to invest in so that we don't suddenly wake up and realize that every single quantum computing company needs a cooling technology, and that's all in the hands of of our adversaries. So we've got to
Right.
think very carefully about the strategic supply chain technologies as well.
And
then what we
can I maybe just interject that there's a very important human capital element to that supply chain. So I think that's an extremely important ingredient as well in the supply chain. Please continue.
Yeah, absolutely. And I think, again, it's interesting, isn't it? Because when we start to invest in these areas, you also see talent crowding in. The question is, what are the most extraordinary undergrads that are coming to our various institutions, whether it's MIT, Virginia Tech, all across the US and the Alliance? They're going to be attracted to places where they see risk capital coming in, where they see exciting companies being started. And so we absolutely have to invest in those sort of resilient, foundational, critical technologies, the supply chain technologies and the key choke point technologies. And then layered on top of that, we think about investing in the technologies of security. So for us, that would mean things like post-quantum encryption and related things, as well as finally more specific defense opportunities. That's more in the realm probably of quantum sensing and other related solutions. But we really are thinking about this defense, security, resilience as a sort of stack, if you like. Now, to get this to work, obviously there are going to be companies who are in material science, in the pharmaceutical industry, potentially in finance or some of the other optimization areas like autonomy or transportation, who are possible lead users, people who are going to write contracts, buy products from these companies. I think we also need the government to step up and send market signals, because investors obviously need to see that markets are emerging. So we have to ensure that our governments are stepping up and saying, we will buy these quantum computers from you. We will produce a contract so that we can work collaboratively with you. And that's a very, very important role for the government. It's not just about the government investing in the early stage research and the talent. It is also about standard setting, but it's also about making markets, actually, so that we can continue to do this investment as effectively as possible.
So both of you have put, I think, a couple of interesting ideas on the table. One is this issue of human capital, and a lot of that turns on how we attract some of the best and brightest minds of the globe, as you were saying, Dave and Fiona, but then keep them, whether it's here in the United States or in the UK or in Europe, instead of sort of forcing them to go back home and go back to the countries from where they came and building their systems there, right? A lot of people have said, look, nobody wants to build their technology in Beijing or in Moscow, and yet we bring some of the best and brightest from the world. And it's not just China and Russia, right? But we bring some of the best and brightest of the world to Oxford and Cambridge in the UK, or to Virginia Tech or MIT here in the US, and then we tell them, hey, by the way, don't stay. You need to go home, and that doesn't seem like the right idea. So I think I want to talk about a little bit about that. The other thing I want to talk about is this idea, Dave and Fiona, that you put on the table about industrial policy and this issue of the government sort of priming the pump and saying we'll be there to create the market. There's a lot of, I think, at times in the U.S. in particular, an anathema to industrial policy. This idea that we don't engage that, we should engage that. It's contrary to the free market. And then you look back at historical innovations at the core of our defense and national security base, whether it's defense industrial base, telecommunications, or the like. And of course, we've invested tremendous amounts of government money in the U.S. in those spaces. And so I'm interested in for both of your views on this question of human capital and government investment, and sort of to take your temperature on that. So let me start with you, Dr. Flammia, and then we'll close out with you, Professor Murray.
Yeah, so I mean, I think it's exactly right. I mean, I've tried to get students or postdocs to work with me who've had visa issues. It's a problem, and it's something that I'd like to see addressed. I'm not sure exactly how we can address that with policy, but there is definitely a human capital bottleneck in our field. It's currently very challenging to hire qualified people in the space for quantum information and not just people who are working on algorithms or theoretical questions, but questions related to specific hardware and things like this. I would love it if we could help that pipeline, give people an easier path to staying here, make it a little bit easier for their families to come and stay. There's no reason why we can't make it comfortable for them to be here too. I've seen a lot of people coming from abroad where their families have to remain overseas. And we can do better than that. There's really no reason we shouldn't do better than that. I feel like it's really a win for the US for us to do that. It's certainly a win for quantum computing if we can do that.
And to your point, Dr. Flammia, it actually creates a situation where if families stay back in their home countries, it allows those host governments to put pressure on the families, right? So in some ways, we think it's actually beneficial to us because we want to keep that relationship going, but in fact, it may actually be counterproductive from a national security perspective.
Yeah, I think that's right. Sorry, now I forgot the second half of the question now.
Oh, sorry, that was my fault. I interrupted you.
Okay.
It was about
right.
industrial policy and the question of whether, in fact, it makes sense to engage in some amount of industrial policy, and whether that's not ahistorical. People tend to think,
Yes,
this is not how America or the West works,
I think you answered that one by looking at the historical track record, right? I mean, when you do look at the historical track record, I think there are plenty of examples where government invests in order to bootstrap some things, and you just have to do that for many things. Quantum computing is absolutely one of these examples. There's no industry. I mean, it's true now. I used to work for Amazon Web Services. There are several other big, large-scale tech companies, IBM and Google being prominent examples. There's a company called Quantinuum, which spun off from Honeywell. They would not have simply started their research into quantum computing if there had not been sustained grant funding at the level of academic institutions for many years, and if that hadn't paid dividends. And now, I mean, I think we can do better than that if we want to actually accelerate the innovation. I think we can, as Dame Fiona said, we can say, look, we will be buying these machines because we want to use them. We want to understand what are their capabilities, what are their limitations, how are people actually going to use them. Let us innovate on them. The way you innovate is you have to actually use the devices. So we can spur that innovation if we think that this is an important area, and there's many reasons to believe that it is an important area. So we should be innovating. We can create these markets. I think that's absolutely right.
So Dame Fiona, you get the last word here. You're right at the heart of this sort of the human capital side at a leading American university, on the investment side and the business side of it at the NATO Innovation Fund. So take us out. Talk to us about this question of human capital on one hand and industrial policy on the other.
Mm-hmm. So I think what we need is to think about human talent, and let's talk about trusted talent, in the same way that we're thinking about risk capital and the need for trusted capital. As you know, with our friends at Paladin, the NATO Innovation Fund, In-Q-Tel, it's a whole group of individuals who are talking together and trying to think about the most effective way to work out how to have safe capital get crowded into the companies and the startups that matter. We talk broadly about the construct of trusted capital. I think it's equally important to think about trusted talent. So what would it take for us to attract the best talent from around the world, make sure that those individuals, when they arrive, are trusted, and to make sure that they can remain that way because they are able to be in our various countries. They can be safe, their families can be safe, and they can actually work to the advantage of all of our nations and not be subject to adversarial influence. I think we have to think about this across the piece. So in the same way that we're thinking about capital across the NATO alliance, across Five Eyes, AUKUS, and our wider Pacific partnerships, the same, I think, needs to be true with respect to the human talent and that trusted talent in the area of quantum. We need to make sure that if we have extraordinary individuals coming, for example, from Denmark or Sweden, the United Kingdom, to the US and back and forth, that we make that more seamless. So it's our domestic talent, but it is also the people that we bring in. Now, when it comes to industrial policy, you're absolutely right. I mean, the US has been engaging in industrial policy for decades, practically for centuries. Silicon Valley is absolutely the product of governments thinking that it's extremely important to invest in everything from early stage radio technology to semiconductors and beyond. The CHIPS Act is obviously an important piece of more recent industrial policy, as is the Inflation Reduction Act. Now, those most recent bits of industrial policy, I think, have been about fixing a problem because we hadn't actually paid attention, and we recognized that we needed to shift some of the industrial dynamics. I think my hope is that for an area like quantum computing, we can do this in a slightly more proactive way. And so we do it by creating the right structures to crowd in trusted capital, to crowd in trusted talent. But we really do still need to create markets. This is deep technology that is risky. It has long time horizons. And so we have to create markets from quite an early stage. I think we will do better when we create those markets at the level of alliances and partnerships, because this way we have larger, more significant opportunities for the companies that we're building and the investors that are investing in them. We have to reduce some of the barriers, so thinking really carefully about how we use ITAR and CFIUS and the sort of range of things that have good intent but sometimes create unwanted friction. But I think a sort of modern industrial policy focused on quantum computing will be able to get us quite a long way if we think about it as an industrial policy for these shared gardens rather than an industrial policy for small yards.
What a great way to end the episode. Thanks so much to Dr. Stephen Flammia and to Dame Fiona Murray from MIT for being here with us today. And thanks to Keelan Wolf and Claude Jennings, the entire NSI CTC staff for the help in producing today's episode. The Control F podcast, including our game-changing technology series, is also on YouTube. So be sure to check out NSI's YouTube page to see our smiling faces and our ongoing conversation. And make sure to join us for our next episode in just 2 short weeks, which will explore cloud and edge computing and now the way it's changing the way we work, the way we store and share and process data across industries ranging from healthcare to national security. And as always, remember, if you like what you heard or saw on YouTube, be sure to rate, review, and subscribe. Thanks all. See you in 2 weeks.